Okay, YouTube, in our last video, we explored solution points to equations in two variables and discussed how the graph of all the solution points really are just showing us the solutions to the equation. So in this video, what we're going to do is focus on just what we call the point plotting method. The point plotting method of graphing, which is really just connecting a series of points from left to right with maybe a smooth curve or a continuous curve that shows all the solutions to an equation. So to break this down, we can kind of look at the different aspects of this, but basically what it comes down to is we always typically want to isolate one of our variables here, and with two variable equations we tend to isolate the y variable. So it's typical to isolate y if we have an xy equation. But what we're going to do is we're going to construct a table of values. We tend to call these like a t-chart or something like that, listing several solution points, and then what we'll do is we'll plot these points and connect these points with a smooth curve or line if it's a smooth curve or a line. So looking at this first equation here, let's go ahead and take a look at what it is I mean by plotting points here and making a table. In terms of making this table here, what we're going to do is we're going to make a t-chart. And I tend to list mine x and then y, but because I have y solved for in terms of x, I tend to look at y as what we call the dependent variable. And so the dependent variable, it's kind of like saying it depends upon what x is. So we actually need to know what x is first, or the independent variable is first, before we can give you a dependent variable value or a y value. So what we're going to do is we're going to just kind of list a nice little battery of x values here. We certainly don't have to use these x values, but all we're going to be doing is really just going and throwing them into the equation in each particular instance. And you'll see that this gets a little bit quicker as you go along. But for this first one here, I'm actually going to show my work. We would say, well, then our y value, what would our y value be? Well, our y value is always equal to -3 times our x value plus 7. So for instance here, we would say that our input is -3. We're going to get a -3 times a -3, which gives us a +9, and 9 plus 7 there. We're going to end up with 16 as our output there. So the point really -3 comma 16 would be on the graph of this equation. Now, continuing this investigation, what if we plugged in a -2? Well, our y value would have been not -3 times -3 plus 7, but it would have been -3 times a -2. Try that again there, -2 plus 7, which gives us, in this case, 6 plus 7 is 13 in this particular instance. So we'd have the point -2 comma 13 on our graph as well. Continuing on down the road here, we'll go a little bit more quickly here. -3 times a -1 would be a 3, and 3 plus 7 is 10. Here we'd take -3 times 0, which is nice because that would get this to eliminate altogether, and we would just get left with 7. And as I'm going through this, I'm also noticing that my output values in this particular case are all going down by 3 every time. So you might hypothesize the next one's going to be 4. Math is, about patterns after all. But plugging this in also, we get -3 times a +1 plus 7, which is really -3 plus 7, which is 4. So for the sake of time here, I am going to go ahead and continue filling these in just with this pattern that I see here going down by 3s every time. But what we're really interested in doing is graphing these points here. So now maybe because I noticed that some of my points went off the graph here, I can change the scale on my y-axis to better fit these in, or I could just graph the ones that I can actually see, which is what I'm going to do here, graph the ones that I can actually see without changing my scale on this first one. So -3 comma 16, since that's so high up there, I'm not going to graph it. As a matter of fact, the first one I'm going to start with is just -1 comma 10, just because I think I can fit this on here. So we'll go left 1 from the origin, up 1, 2, 3, 4, 5, 6, 7, 8, 9, and actually 10 is right here. So we have -1, 10. We also have 0 comma 7, so 2, 3, 4, 5, 6, 7. We also have 1 comma 4, so over 1 up 4, over 2 up 1, and then we have the point 3 comma -2. So one thing that needs to be mentioned here is essentially this. Just because I did not graph, say, these 2 points right here doesn't mean that they're not on the graph. It just means that I couldn't fit them in the window that I had right here. So it's always good to list anyways any values that you have, because even if they don't fit, they are solution pairs. Also this, because I plugged in these x values doesn't mean that they're the only x values that actually work in this equation. As a matter of fact, the question I'd ask you to think is, are there any x values that when you plug it into this equation you wouldn't get a y value back? And really, we can always take -3 times an input and add 7 to it and get a y value back. So that being said, we can see that this pattern is going to continue to happen, and therefore what we can do is we can actually just connect the dots on this graph, and all of these intermediate points that you're seeing on this graph as well are also solution pairs to this equation. So the last thing I want to make sure we do here when we sketch this is actually take the time to write the equation next to the graph that you've sketched, because what you're saying is this is the set of solutions to y equals negative 3x plus 7. So before we piece out of this video, what I want to do is I kind of just want to look at a pattern here that is quadratic in nature. And so the last graph that we looked at was a line. It was a linear graph. What would happen if we had, say, y equals x squared minus 2? So again, going with these steps over here, we'd say we'd want to isolate y. Y is truly already isolated. So we have x squared minus 2. And filling out our table here, it looks like we could just, choose a nice set of input values here, negative 3, negative 2, negative 1, 0, 1, 2, and 3. So we're going to plug these in one at a time here, starting with this first one. Looks like we get y is equal to our x value squared minus 2, not plus 2, and our x value here in this case is negative 3. So to plug this in here, it looks like we get negative 3 squared, which is a positive 9, and a 9 minus 2, which gives us actually an output of 7. Looking at this next one also, we'd say x squared minus 2. In this case, we get 4 minus 2, which actually gives us just 2. How about if we squared a negative 1? Well, squaring a negative 1 gives you a positive 1, and 1 minus 2 gives us a negative 1. If we plug in a 0, we just get the negative 2. And the neat thing about these is as you plug in the positive x values, like 1, well, 1 squared minus 2 is the same thing as negative 1 squared minus 2. We get negative 1. When we plug in a 2, we get the same thing as when we plugged in our negative 2. Because we're squaring it, it makes it positive. We actually get 2 squared, which is 4. 4 minus 2 is 2. And then last but not least here, we're going to see that if we plug in 3, we get the same thing as when we plugged in negative 3. So we're going to put a 7 here. And then just plotting all these points, I guess just start with negative 3, 7 here. Negative 3, 7 would be left 3 up, 1, 2, 3, 4, 5, 6, 7. So we'd have a point here, left 2, up 2. So negative 2, positive 2, negative 1, negative 1. So negative 1, negative 1 would be down here. 0, negative 2 would be here, and then we start to see this level of symmetry here. 1, negative 1, 2, comma 2, and then 3, comma 7 here that occurs. And so what we get is actually this U-looking graph, and if you can think of the name of this graph, good for you. It does start with a P. So if you haven't thought of it yet, here we have a parabola. But this parabola that's symmetric about the y-axis in this case. Easy to make a sketch of this graph just by making a table. Cheers.